discussed? Up to which topic we discussed in the last class?
So I think suspension insulator.
Suspension insulators. Okay. Did we start suspension insulator, or before suspension insulator we stopped our discussions?
So we did up to disc insulator, pin insulator,
Pin and disc.
pin and disc, yeah. Remaining suspension and strain is left.
These things, breakdown of insulators we discussed. Dry flashover, wet flashover and puncture, etc. These things we discussed. And also the insulating material we discussed, glass and porcelain. Did we discuss that?
Yes, sir.
Advantages of glass insulators also we discussed.
Yes.
Type of insulators we started. Pin insulator we discussed. And these things we also discussed. Disc insulators I think we discussed. Suspension insulators we didn't discuss, I think. Did we discuss these things or not?
No, sir.
Okay, so let us start with suspension insulators. Now in the last class we have seen that we have, so far as high voltage engineering is concerned, 4 or 5 different types of insulators which needs to be discussed. Those 5 types of insulators are pin type insulators, disc type insulators, suspension insulators, train insulators, and post insulators. Now, among these 5 types of insulators, we discussed in the last class pin and disc type of insulators. Now, today we have to discuss suspension type of insulators. Now, actually, both pin type or disc type insulators, their use are limited to a certain level of high voltage. Actually, as here in the slide, the first point says beyond 33 kV pin type insulator is uneconomical. Yes, that we also discussed in connection with the pin type of insulators. Now, actually, you must have seen while traveling through a train, by a train, or even by roads in rural areas, or sometimes in Kasbah areas, you will also see that high tension lines. In Kasbah area, we have one HT substation of WBACB. Earlier it was WBACB, now it is WBACGCL, West Bengal State Generation, State Electricity Generation Corporation Limited, etc. So there we have a HT substations from where HT transmission lines are actually transmission lines run in either direction. If you have carefully seen that, you must have noticed then that high voltage conductors are suspended from the tower cross arm with the help of suspension, with the help of suspension type of insulators. Now, this suspension type of insulators actually is supported at the top from the tower cross arm, and at the bottom, the suspension insulator, they actually support the HT transmission lines. So, in this way, at the lower end of the suspension insulator, high voltage is there, and at the top end or upper end of the suspension insulator, earth connection is there. So, in between these two nodes or points or terminals, whatever you call, 2 voltages are supported. One is live potential, and the at the bottom end, and at the upper end it supports the earth potential, or it is connected to earth potential. Now, a string of suspension insulator is formed by joining the disc insulators together. If we go back to the diagram of disc insulator, you will see this is the high voltage electrode at the lower end of the disc insulator. Just a minute. এখন ক্লাস নিচ্ছি পরে নটার পরে নটার পরে Now these disc insulators are joined together to form a string of suspension insulator. That is, the units of suspension insulators are basically the disc insulators. Actually, how it is connected, that also we mentioned in the last class. This high voltage electrode, the spherical portion of the high voltage electrode is placed in the top cap of the next disc insulator. Likewise, the number of discs are joined together to form the suspension insulator, and in this way the adequate insulation level is provided. Here you will see that for 132 kV line, 11 to 13 disc insulators are used, whereas for 230 kV line or 220 kV line, 18 to 20 such disc insulators are required. Now let us see a diagram. Suppose this is the transmission tower. These are the suspension insulators as it is seen from the diagram. These are the strings of suspension insulators, these ones. And at the lower end or bottom end of the suspension insulator, the conductor, HT conductors are supported. And this is the tower cross arm from where the suspension insulators actually hang. And at the upper end or top end of the suspension insulator is connected to the tower cross arm. That is, in other words, we can say that at the top end, the suspension insulator is connected to arc potential. And at the lower end, it is connected to live potential. And this is the ground wire which is placed at the top of the transmission tower. So this is how the suspension insulators are formed. Now, why do we go for, or why do we opt for suspension insulator instead of making a suitable pin type insulator, so that we can that same level of voltage can be accommodated? But actually, the suspension insulators, they provide certain advantages over the pin type insulators, and those advantages we shall now discuss. Let us write advantages of the suspension insulator. Just a minute. Now, the first point, as it says, that each insulator, I mean, here insulator means each disc insulator, is designed, here we should specifically mention the word disc. Each disc insulator is designed for a relatively or comparatively low voltage or low working potential of the order of 11 kV or so, and the insulation for any required voltage can be obtained by using a string of suitable number of discs. That is one advantage, that individual discs need not be developed or manufactured for higher voltages. The discs will be of relatively lower or low working potential of the order of 11 kV or so. In the event of failure of an insulator, only the defective unit instead of the whole string has to be replaced. That is one important point. Now, if we had used a single pin type insulator in place of suspension insulators, then in the event of failure, the entire pin insulator would have been, or the entire pin insulator could have been replaced or would have been replaced. But here, what happens in the event of failure, if you can identify or detect in which unit or across which unit the fault or has developed or failure has taken place, then you can very easily isolate that single unit instead of replacing the entire unit or the whole string. So that is one advantage. Next advantages are, in the event of an increase in operating voltage on the line, yes, if due to some reason the line, the particular transmission system where a suspension type of insulator has been used, if the transmission level voltage of that transmission system increases due to some reason, then what will happen? In the case of a single block pin insulator, that insulator must be replaced, because the same insulator cannot withstand higher voltage level. But here in the case when we go for suspension type of insulator, then instead of replacing the entire unit, we can very easily add one or two additional discs in the string so that it can accommodate the increased voltage level. That is another advantage. Also, the mechanical stress. This somebody wants to join, I think. Rajorshi Bhattacharya. The mechanical stresses are reduced since the line is suspended flexibly. Yes, at the bottom where it supports the transmission conductors, and also at the top from where it is suspended from the tower cross arm, in either side, either at the lower end or at the upper end, the insulators are suspended flexibly. That is why the mechanical stresses are reduced here. With pin type insulators instead, what happens? A rigid nature of attachment results in fatigue, causing ultimate brittleness of the wire, induced due to alternating nature of stress. Yes, since the supply voltage is alternating, that stress that is developed is also alternating in nature. So these are the major advantages of suspension insulators. Why do this explains why instead of using a single piece of pin type insulator, people always prefer using suspension insulators. Do you understand, or do you have any other question? Any question up to this point? Do you understand?
Yes, sir.
Okay. Now strain insulators. Normal suspension insulator cannot take the horizontal tension where the line has sharp bending or where the line terminates. Suppose at a particular transmission tower, one line has to be terminated, or from that particular transmission tower, the line will take another bending. It will change the direction of run of the transmission line. In that case, in those cases, with the help of normal suspension insulators, we cannot connect the lines or with that particular transmission tower. For that purpose, strain insulators are used. Again, these strain insulators are again made up of disc insulators, but their designs are slightly different from those of suspension insulators. What really happens? We cannot terminate any transmission line directly onto the tower body or tower cross arm, whatever, because that will result in dead short circuit. Live high voltage potential will come to earth contact, and that will result in dead short circuit. That is why we have to terminate them with the help of insulators, and for those purpose actually strain insulators are used. As it is shown in the diagram, this is one incoming line and this is the outgoing line. Maybe the outgoing line is running in the or will move in some other direction, not in the same direction, then what happens? We have to terminate the line, incoming line, with the help of insulators at this tower body, and from here again the line has to be taken to some other direction, but there has to be some continuity between the incoming line and the outgoing line. That is done with the help of a connecting wire like this. But in between the connecting wire and the tower body, another set of insulators are provided, which are normally called the jumper. Now, these jumper is provided. Actually, if you just leave the connecting wire just as it is, then in the case of strong wind or adverse weather condition during storm, it may so happen the actually this connecting wire will oscillate vigorously, and if the wind is very strong, then it may come in direct contact with the tower body, resulting in direct short circuit. That is why these jumpers are provided, just to increase the weight of the overall system so that it cannot oscillate so much. This is the purpose of providing the jumpers. Next is post insulators. Now, unfortunately, I think you didn't get any scope to visit high voltage laboratory physically till now. Has anyone of you visited the high voltage laboratory, except for the fact that you might have visited the high voltage laboratory during your first day in Jadavpur University? Maybe. I am not talking about that. After that, for any lab purpose or some other purpose, have you ever visited or entered the high voltage laboratory? Did you get that opportunity?
Yes, sir.
When?
Offline lab classes that was held on 21st December.
Oh, then very few of you came, I know. Yes. There, have you seen any post insulators of this form? No, I think you didn't notice actually. Really, what happens in high voltage laboratory, many times you have to deal with high voltage electrodes, right? Now, this is not really high voltage support. This is high voltage electrode. I'll make the correction in the note what I shall send you. And depending upon the operating voltage of the high voltage electrode, a suitable clearance from the ground has to be maintained. We cannot simply put the high voltage electrode on the ground or even very near to the ground. If the high voltage electrodes are placed very close to the ground, then there may be a flashover between the high voltage electrode and ground. That is why, in order to hold the high voltage electrodes, these post type of insulators are used. Now, you see these post insulators, they're, two side surfaces are not simply plain surfaces or smooth surfaces. Instead, the two surfaces are actually corrugated. Now, actually, since this is your high voltage electrode and this is the ground, obviously along the surface, external surface of the post insulator, some current will flow from high voltage electrode to ground, and that is the leakage current. Now, in order to reduce the leakage current, what all you have to do is you have to increase the length of the leakage current path, and that leakage current path is increased. Length of the leakage current path is increased by providing these corrugations, so that the leakage current has to travel through longer length. That is one thing you must take note. And another thing is this high voltage support or high voltage electrode is not directly placed on the corona shield, but instead it is placed on a corona shield. Why? Actually, if this corona shield was not present, then what would have happened? Electric field lines coming out from the high voltage electrode would have been or would have terminated at the ground. Now, obviously, there would have been a crowding of electric field lines near this point or near this point or even around these sharp points. Now, if you use another conducting material and place the high voltage electrode over it, then the entire arrangement is at the same high voltage potential or high potential. Then the field lines coming out from the entire arrangement will not be crowded around any sharp point or any point, but it will be more or less widely distributed. And if we can avoid crowding of electric field lines around any point, then what will happen? Then the chance of ionization of air around that particular point will be reduced. In order to avoid the formation of, or in order to avoid commencement of ionization of air, that is the reason why corona shield is actually used. Do you understand this process? It is also mentioned over here, corona shields are not area. Corona shields are generally employed to increase the equipotential area and reduce the electric stress near the high voltage terminal. So do you understand this process? This point? Why corona shield is used?
Yes, sir.
Okay. Then let us discuss insulator profile. Now, insulator profile. Pin and other type of insulators are so designed that the surface of the shades, what do you mean by the shade? For example, if we consider this insulator, this is Sacral type of insulator. Anyway, these portions, the portions which are bulging out, they are called the shades, rain shades sometimes. And this part, the body of the insulator, cylindrical portion, they are called the stem. Right? Insulator profile are so designed, pin and other type of insulators are so designed that the surface of shades becomes equipotential so as to have less leakage current. Yes. Now you see, if you look at the arrangement of any insulator, maybe pin type or disc type, this is your high voltage conductor. For any type of insulators, maybe pin type, disc type, we have seen there is a top groove over which the insulator is placed. Pin type insulators, or particularly, there is a top groove. If we go back to the diagram, yes, this is the pin type insulator. This is the conductor groove. So here we place the high voltage conductor, and this is the metallic pin through which it is placed at the tower cross arm. That is, it is connected to the ground potential at the lower end. Therefore, if we go back to the profile, so through that top groove, considering the pin insulator, through through the top groove of that insulator, the conductor will run. And this is the pin which is placed inside the body of the, or inside the stem of the insulator, which is at ground potential. Therefore, the field lines will be distributed like this. Starting from the live conductor, it will terminate at the ground potential. And we know the equipotential lines and field lines are at right angles. Therefore, it is always, the insulators are designed so that the rain shades always lie along the equipotential lines. They are parallel to the equipotential lines. If we can place or develop the insulator so that the rain shades lie along the equipotential lines, then what will happen? On the equipotential surface, we know no current can flow. Similarly here, if we can design and develop the insulator profile in such a way that the rain shades lie along the equipotential lines, or equipotential lines lie along the rain shades, then leakage current, theoretically at least, will not be flowing along the rain shades. In this way, though we cannot make the leakage current completely zero, but we can reduce the magnitude of the leakage current to a great extent. So this is why, or this is how the insulators are designed and developed. Is that okay? Do you understand this point?
Yes, sir.
Okay, next is Sacral type of insulator. Sacral insulators are very commonly used in low voltage system or distribution lines. They serve the purpose same as that of the pin insulators in the case of HT lines. These insulators are also known as spool insulators. Sacral insulators are used at the end of the distribution lines or at sharp turns where there is excessive tensile load on the lines, and also to hold the conductors at the top, as in the case of pin insulators. These insulators can be mounted either in the vertical or horizontal position. That is the difference from the pin insulators. Pin insulators can be or has to be mounted in the vertical position always, but the Sacral insulators can be mounted in either horizontal or vertical positions. That is why they are normally used to support the distribution lines at the end of the distribution systems distribution lines at a particular distribution pole or tower, whatever you call it, or where there is a sharp turn. This is the diagram of Sacral insulator. The Sacral insulator is mounted axially. The loading is on circumferential grooves. These are the circumferential grooves in the insulator. The conductor is secured in the grooves by means of soft bending wires. Yes, it is placed on the top groove, and through the soft bending wire, they are tied in the side grooves. The insulators are bolted to the tower cross arm of the pole. Yes, this is how the Sacral insulators are used. But since it is very frequently used, that's why I just mentioned it, but it is not really coming into the category of HT insulators. Next is form factor of insulators. Form factor of the insulator can be defined in either of the two ways. One is integration of over the length of the insulator, 0 to L. L is the entire creepage length. Then integration over the entire creepage length, dl by pi into dl, where d suffix l is the diameter at a creepage length. Then pi dl will give you what? What is pi dl then?
Circumference.
Yes. Elemental creepage at a point, that is dl. to that of circumference at that particular point, integration of which over the entire trippage length gives you the form factor. That is one way. The same thing can be expressed in terms of height as well. That is mentioned in the next lines. Form factor is equal to dh by pi dh, where dh is the diameter at height h. Is it okay? Do you understand up to this? Any question up to this?
No, sir.
Okay. Next, we shall discuss voltage distribution in suspension insulators. Suppose we consider transmission system where the transmission lines in 3 phases are supported with the help of suspension insulators as shown in the figure. And there is a ground wire at the top, etc. Now, since these insulators are connected to the ground potential at the top and connected to live potential at the bottom, in between any two discs, there is a metallic pin through which upper disc is connected to the lower disc that we have seen. Do you remember that? How suspension insulators are formed?
Yes, sir.
Therefore, we have between two live potentials, insulators and metals also, both. Therefore, we all know that whenever a dielectric material is separated by, two electrodes are separated by a dielectric material, and if the electrodes are maintained at different potentials, a capacitance is formed in between. Likewise, here also, for each disc between live potential, ground potential and live potential, corresponding to each disc, one capacitance will be formed. Let those capacitances are C prime. That is equal to M into C. What is M? We shall explain. Similarly, since between any two discs there is a metallic section and which is held at some potential, what is the potential we do not know, but it will be subjected to some potential. It will not be at ground potential, nor it will be at live potential. Therefore, another group of capacitances will be formed between these metallic sections and the tower body through air. Air is another dielectric here. Do you understand the formation of the capacitances here between tower body and the metal pins here through air?
Yes, sir.
Okay. So, this insulator arrangement, suspension insulator, can be represented with its electrical equivalent circuit like this. since the insulators used in discs are identical, therefore the capacitances which represents the insulators are all identical, C prime, C prime, C prime, C prime. Similarly, the capacitances formed between the tower body and the metal pins here, they will also be identical so long as the distance between these metal pins and the tower bodies remains same. And that usually happens. They are suspended vertically, so the distance between them and the tower body will be identical to each other. Therefore, if that happens, then all these capacitances will also be identical. Let that be C, capital C. Do you understand up to this? Somebody should tell me whether do you understand this or not.
Yes, sir. Understood.
Understood. Why so feebly you are telling? Any query or any confusion?
No, sir.
Okay. Now you see these points in the suspension, these we have already discussed, C prime and C, what is actually that just these capacitances, C prime, that is the capacitances of corresponding to the disks, they are referred to as mutual capacitances, but in some references or in some books, they are also referred to as self-capacitances, but we shall mention it as mutual capacitance. And the capacitances formed between the tower body and the metal pins are normally called the ground capacitances or shunt capacitances. Okay? And now you see, here, let the ratio between the mutual capacitance and ground capacitance be M. Therefore, C prime by C is equal to M, or C prime is equal to MC. That we are assuming. Again, going back to the diagram, this is the voltage distribution at any instant of time, V1, V2, V3, V4. These are the voltages available across the individual disks. And let the total voltage be V. So if we consider the instantaneous values, then we can write at any instant of time when this is the voltage distribution, V is equal to V1 plus V2 plus V3 plus V4. As it is written over here. Again, net charges at node 1, 2 and 3, node 1, 2 and 3 has to be 0 since they are not connected directly to any supply or any source of energy. Do you understand this point?
Sir, can you please repeat?
Yes. If we consider these nodes 1, 2 or 3, they are not connected to any supply system or source of energy directly. But this node is directly connected to the high voltage electrodes. So at this node, there will be continuous supply of charges. But at this node or this node, what will be the net charge? Will there be any accumulation of charges since they are not connected to any source? the amount of charge that should enter here, that will enter node 1, must go out through these two parallel paths?
Yes, sir. According to KCL.
According to KCL. So there will not be any accumulation of charges. That point has been mentioned over here. Net charges at nodes 1, 2, and 3 will be 0, as these nodes are not connected to any supply source.
Yes, sir. Understood.
Then the amount of charge entering node 1 will flow to the ground through shunt capacitance and mutual capacitance connected to node 1. So here, the charges may come from bottom, and enter node 1, but whatever amount of charge enters node 1 will flow to ground via the mutual capacitance and ground capacitance. Therefore, if we write down the Kirchhoff's current charge equation or from charge balance equation using Kirchhoff's law, what we can write? What is the amount of charge entering node 1, that is M into C into V, Q is equal to CV. What is the C? What is C here? C prime, that is MC. MC into V2. MC into V2 is the charge that will enter node 1. And what will be the charges what charge will leave from node 1? One is MC into V1 and the other is C into V1. So can we write this equation? MC V2 is equal to C V1 plus MC V1.
Yes, sir.
From where what we can write? V2 is equal to
M plus 1 into V1.
this MC V2. Therefore, V2 can be written as, if we divide both sides of equation A by MC, what you can write? V2 is equal to V1 plus V1 by M, or 1 plus 1 by M into V1. Can we write that?
Yes, sir.
Similarly, if we apply Kirchhoff's current law in terms of charges at node B or at node 2, not B, what we can write? The amount of charge entering node 2 is MCV3. That should be equal to what? MCV2 plus C into V1 plus V2.
Yes, sir.
Okay. MCV3 is equal to MCV2 plus C into V1 plus V2. That is our equation B. Similarly, at node 3, this can be written MCV4 is equal to MCV3 plus C into V1 plus V2 plus V3. From A, it may be written that we have verified V2 is equal to V1 plus V1 by M. From B, it may be written V3 is equal to V2 plus V1 plus V2 by M. And from V4, we can write this equation 3. I think there is no confusion up to this. Up to equation 3, is there any question or confusion? Please tell me. Is there any query up to equation 3? Is there any question?
No, sir.
Okay. Then We shall continue these equations. Now, our next step will be to express V2, V3, and V4 in terms of V1. That you try yourself. I take 5 minutes break here. After coming back, we shall deduce or we shall verify whether you have correctly arrived at the expressions or not. V2 we have already expressed, that is V1 into 1 plus 1 by m. Similarly, V3 and V4 can also be expressed in terms of V1. So it is my request to you all, within 5 minutes, you just try to deduce or express V3 and V4 in terms of V1. Let us resume our class. Could you find out the expressions for V3 and V4 in terms of V1?
Yes, sir.
So 1 plus 3m plus m squared into V1.
Just I am showing you. So V3 is this, which upon simplification comes out to be what you said. V3 is equal to V1 plus into 1 plus 3 by m plus 1 by m square. And V4 is like this. V1 into 1 plus 6 by m plus 5 by m square plus 1 by m cube. So thus we could express all the voltages V2, V3, V4, etc. in terms of V1. Similarly, had there been more number of discs connected in any string of suspension insulators, those voltages appearing across the different discs can be expressed in terms of the voltage V1. Again, going back to the expressions, basic expressions here, V2, V3 and V4, it is seen that every V2 is V1 plus V1 by M. Now M being less than normally, what should be the value of M? Whatever maybe, it cannot be negative. M is always positive, greater than or less than 1, that we shall discuss afterwards. But whatever may be the value of M, V2 is V1 plus some fraction of V1. Therefore, V2 is always greater than V1. Likewise, V3 is V2 plus some fraction of V1 plus V2. So therefore, V3 will be even greater than V2, and likewise, V4 is always also greater than V3. Therefore, this point can be mentioned that from the 1, 2 and 3 equations, it is obvious that V4 greater than V3 greater than V2 and V1. That is, this is important. As we move towards the live conductor, the potential across the discs increases. The maximum potential will be across the disc connected to the high voltage terminal, and the minimum potential will be across the disc connected to the cross arm at earth potential. That is important. This point is important. The above relations are also valid for RMS values as they satisfy instantaneous voltage distribution. So these 2 points, I think you well understand. Do you understand, or do you have any question about these points? That is the distribution of the voltages. Minimum voltage will occur across the disc connected to the tower cross arm directly, and the maximum voltage will appear across the disc connected to the live conductor directly. Do you understand this point or not?
Sir, understood.
Okay. Next is then, there is a problem. Can you try to work out this problem? Calculate the maximum voltage across a string of suspension insulators as shown in figure below. If the maximum voltage per unit cannot be allowed to exceed 17.5 kV. Now here in this problem, MC is 8 into C. So what is the value of M then? Mutual capacitance
8.
by 8. Therefore, we know 8. So V2 is equal to V1 plus 1 by V1 plus, not plus, V2 is equal to V1 into 1 plus 1 by 8, which comes out to be what? 1.125 V1, isn't it?
Yes, sir.
And what about V3? V3 is equal to 1 plus T by M plus 1 by M square into V1. So in terms of V1, what we can write if when M is equal to 8, so find out that 1 plus 3 by 8 plus 1 by 64.
Sir, V3 equals to 1.39 V1.
1.39 V1. So these are the three voltages in terms of V1. Now we have already seen that the maximum voltage occurs across the disk nearest to the conductor. So the maximum voltage per unit cannot be allowed to exceed 17.5 kV, and that occurs across the disk nearest to the conductor. Therefore, V3 should be equal to 17.5, that is 1.39 V1 is equal to 17.5 kV, from where we can find out V1. What is V1?
V3 is 1.83 V1.
Yes.
1.83 V1.
Which one?
V3.
No, it will be 1.39 V1. You find out this.
Okay.
Yes, 1.39.
1.39 V1. So 1.39 V1 is equal to 17.5. Therefore, V1 is equal to, from here, you can find out V1. That step is missing anyway. You find out V1, 1.39 V1 is equal to your 17.5. So what will be V3 is equal to 17.5, that is 1.39 V1. So V1 can be determined from here.
Sir, V1 equals to 12.58 kV.
No. V1 is equal to 1.125 V1 and V2 is equal to this. So if what is V1? V1 is equal V1, let me find out.
Sir, 1.39 V1 equals to 17.5 kV.
17.5
So from this
divided by
V1,
1.39, 12.6 or 12.58.
yes, sir, 12.58.
That is your V1. And then V2 will be equal to what? That multiplied by 1.125.
14.15.
14.15 kV. Therefore, total voltage V1 plus V2 plus V3 will be sum total of these three. Let that be your 44.23 kV. Now, this is the voltage from the live conductor to ground. And the line voltage will be equal to √3 times of that, 76.6 kV. Agreed? Agreed? 76.6 kV?
Yes, sir.
Okay. Next, mechanism of failure of suspension insulators. Now, the bottom insulator nearest to the live conductor experiences maximum voltage drop. Hence, electric stress is maximum across the disk, across this disk, and flashover of the string takes place initially from the bottom insulator disk in case of overvoltage. In the case of overvoltage. Okay, so since maximum voltage and stress develops across the disk nearest to the live conductor, so flashover starts initially across the disk, across that particular disk, that is the lowermost disk. And when complete flashover takes place across that particular disk, the entire voltage, live potential, is then transmitted to the next disk, and that particular disk is subjected to overvoltage, and flashover occurs across the second disk from the bottom. In this way, the live potential is transmitted to the other disk and it moves in the upward direction, and finally, the complete failure of all the insulators, I mean in terms of flashover, occurs and the live potential is directly connected to ground. And when it causes actually total flashover of the insulator and a dead short circuit. Do you understand the process of failure of the suspension insulators? Do you understand or not?
Yes, sir. Understood.
Understood. Next is string efficiency. String efficiency of any suspension insulator can be explained or can be defined as the measure of uniformity, or in other words, non-uniformity in the voltage distribution across the string of a suspension insulator. The more the string efficiency, the more will be the uniform potential across the disks of a suspension insulator. Now, there are three ways by which we can actually define or the string efficiency. The first one is this: string efficiency is equal to voltage across the whole string divided by number of disks multiplied by the voltage across the disk nearest to the conductor. That is one. Alternatively, it may be expressed as voltage across the whole string divided by number of disks to the maximum voltage across any disk. And usually, at least under ideal condition, the maximum voltage must or should appear across the disk nearest to the conductor. So it is just another way of stating the relationship in the first case, that is voltage across the disk nearest to the conductor. And the third one is flashover voltage of the whole string divided by number of disks into flashover voltage of a single disk. Now, since we are using identical disks, flashover voltage of any disk should be same. Therefore, that is another way of expressing the string efficiency. Do you agree? Do you
Yes.
agree?
Yes, sir.
Okay. Now, just by this time, you have understood that the string efficiency is not 100%, or the voltage distribution is not uniform. Therefore, there has been consistent effort to improve the string efficiency and to make the voltage distribution across the string of suspension insulators as uniform as possible. So, let us now discuss that. Now, what are the reasons for, or what is the main reason for non-uniformity in voltage distribution across the string of suspension insulators? What do you think? Can anybody tell me that?
Can you repeat the question?
My question is, why the voltage distribution is not uniform across the string of suspension insulators? Why it is not uniform? What is the reason?
So because of the shunt capacitances.
Yes, it is because of the shunt capacitances. Had there been no shunt capacitance, then there could no branching of current, or no current would have flown to the ground through those capacitances, and at different link pins, no since there were, in the absence of shunt capacitances, no current could have flown anywhere else, then the entire current that enters from the lowermost disk has to flow through all other disks. But it is not really so because of the existence of shunt capacitances. And due to the presence of shunt capacitances, some current always flows to ground from the link pins, that is the nodes, through the shunt capacitances. Now, in order to improve the voltage distribution across the string of suspension insulators, what all you have to do is you have to either reduce the effect of shunt capacitances, or in other words, if you can improve the flow of current through the different disks, then also it is possible, because the voltage drop across the disks or units is basically equals to the current flowing through them multiplied by their capacitive reactances. Now, since the disks which are used are identical, their capacitive reactances are same. Therefore, if you cannot improve the magnitude of the current flowing through them, you cannot improve the voltage distribution. That is why it has been mentioned here that in order to improve the string efficiency, or in other words, to reduce the non-uniformity in voltage distribution around a suspension insulator, effort should be made to have higher value of the ratio between the mutual capacitance to the ground capacitance, that is M. Since M is the ratio between capacitance of each unit to the shunt capacitance, so either the value of the unit capacitances are to be increased, or the value of the shunt capacitances are to be decreased. These are the two ways by which we can improve the voltage distribution of across the suspension insulators. I think you understand these 2 points. One way is use of longer cross arms. Here, if you use longer cross arms, then the distance between the tower body and the pins of the suspension insulators will increase, and capacitance is basically epsilon A by D. Since epsilon remains same, the insulator unit is placed in air, and cross-sectional area also remains the same. So increasing the distance between the two electrodes, we can reduce the value of the capacitance. That is one way. Do you understand this point? And in order to increase the distance between the tower body and the pins of the suspension insulators, what all we have to do? We have to use longer cross arms of the tower. Do you understand this point or not?
Yes.
But if once you go for longer cross arms, the cost of the tower increases. So this solution, though this provides a solution, but it is not economically feasible solution. So we have to go for other methods. The next method is use of graded units. In this method, what is done is longer discs or discs of higher capacitances are used towards the line end. Why? Why longer discs or discs with higher capacitances are used towards the line end?
So because voltage is higher in there, so to make the voltages
It's basically I into XC, isn't it?
Yes.
So if C is higher and XC is equal to 1 by omega C, so if C is more, XC will be less, isn't it?
Yes, sir.
And lower voltage will be available across the line end, and higher voltages will be available across the ground end. That is because as you move away from the line end, current gradually decreases. So to keep the voltage drop same, when current decreases, you have to increase the capacitive reactance, and that you can do by reducing the value of C. So lower discs or smaller discs has to be used towards the ground end, and larger discs has to be used near the live end. Do you understand this point? Or not? You tell me.
Yes, sir.
Okay. But even this method provides some improvement in voltage distribution. It is also not really a very practical method, because in the case you use different sizes of discs at different locations, then in your stock, instead of keeping a single type of discs, which is normally done when you use similar or identical discs everywhere, that flexibility is lost. You have to go for different, or you have to keep in your stock different types of discs, so that in the event of failure, you can replace the particular disc by its proper size of disc. That is another disadvantage. In the case of failure, you have to first identify which particular disc of and that of what size has been damaged, and that particular disc you have to replace. But in the case of suspension insulators made up of identical discs, flexibility is much more. You don't have to be bothered about the size of the disc. You just have to identify and locate the faulty disc, replace it by any one of the available discs in your stock. Now here, if you even then use this, how the voltage distribution develops and voltage becomes uniform, that can be verified here from this figure. Here we have assumed that after using different types of discs, the ratio between the mutual capacitance and shunt capacitances are not identical. Obviously, that will be varying. Now, that is why it has been written A1C, A2C, A3C, A4C, A5C, etc. And the voltages, but here we assume that all are identical. Now, again, applying Kirchhoff's charge balance equation here at node A, what we can write? A2C into V, that is equal to A1CV plus CV. Therefore, what we can write from here? A2 is equal to A1 plus 1. Can we write this? From here, A2CV is equal to A1CV plus CV. From here, we can very easily write A2 is equal to A1 plus 1. Yes?
Yes, sir.
Similarly, at node B and C, if we apply the same method, Kirchhoff's charge balance equation, we can write these expressions. A3 is equal to A2 plus 2 and A4 is equal to A3 plus 3. And in general, what we can write is this: AN plus 1 is equal to AN plus N. Okay? Can we move to the next slide? Okay. Now let us discuss this method of improving string efficiency. Now here, these problem points we have already discussed. So let us now discuss this. Static shielding by grading ring. One way of improving string efficiency is increasing the values of the capacitances of the disks and decreasing the earth capacitances. The other way is compensation for the charges passing through the to the earth capacitances. This is done by using a guard ring or grading ring. Here the arrangement is like this. At the lower end, instead in addition to the transmission conductor, a large diameter metallic ring is connected, which is maintained at the same potential as that of the transmission conductor. And as a result, it is maintained at the same potential. Actually, a set of capacitances are formed between the link pins between the disks and this metallic ring. Let these capacitances be C1, C2, C3, C4, and C5, as it is shown in the figure. And we have seen that we are using identical disk insulators. Therefore, the mutual capacitances are all MC and earth capacitances are C as before. But here we assume that with this arrangement, we are able to distribute the voltages uniformly across the disk of the suspension insulators, and those voltages BP. Next is then, let the capacitances formed, etc., C1, C2, C3, C4, C5, etc., considering the charge balance at point A. Let us go back to the diagram. What we can write at point A? What are the charges entering node A? One is MCV as before. And what is there any other charge that enters node A? Yes, obviously. Here is the capacitance which is formed between the link pin and the grading ring. So, and the grading ring is maintained at live potential. So, some charges will be flowing through this capacitance to this node A. And the magnitude of that charge can be found out as equal to, if we assume that the n number of disks are there, then the total voltage is n into V. At this point A or at this node A, what is the voltage? N into V minus V. That into C1 is the amount of charge that is entering node A. Therefore, M into C into V plus N minus 1 into CV, that should be equal to the charges that are going out, that is M into CV plus C into V. That is what written over here. M into CV plus CV, those are the outgoing charges. That is equal to MCV into N into V minus V into C1, from where we can write C1 is equal to C by N minus 1. Do you understand this point or not? Tell me. Tell me, please, whether you have understood this point or not. Somebody should tell me whether you have understood this derivation up to this point. C1 is equal to C by n minus 1 or not.
Yes, sir.
Okay. Similarly, proceeding in the same manner at point B, we can write this equation. MCV into C into 2V is equal to MCV plus N into V minus 2V into C2. From where we can write C2 is equal to 2C by N minus 2. Similarly, C3 can be written as equal to 3C by N minus 3. And in general, then we can write Cp is equal to P into C by N minus P. Thus, if the ring can be arranged such that the capacitances C1, C2, C3, C5, etc. are formed according to equation 1, all the voltages across the mutual capacitances will be the same and the string efficiency will be maximum. Arcing horn or ring. Yes. Now you see, this is one suspension insulator. Sometimes you will see that at the top of the insulator, also at the bottom of the insulators, two rings or horn, which are also called horns, with sharp ends are provided. The upper ring or horn is connected to ground potential and the lower ring or horn is connected to live potential. This is done because of the fact that in the event of failure, we have seen that it starts from the lowermost disk. Then it extends in the upward direction and finally bridges up the high voltage and earth electrodes. Now, this is because of the fact that the voltage and also the stress initially exceeds the ionization strength or breakdown voltage of air across the lowermost disk. Now, when you provide these two horns with sharp edges, the voltage across the sharp points or sharp edges will be much higher. And obviously, in the event of over voltage, the flashover or ionization of air will start from the or around these sharp points and will extend towards the other horn or disk to air. Thereby, they will not, if these horns are provided, they will not allow the surface flashover to occur near the insulators, but instead away from the insulators through air. Thereby, it will protect the insulators. Also, sometimes the lower arcing horn plays the same role as that of the grading ring just now we have discussed. So these are the points you just quickly go through. Now this tracking we discussed in the case of insulators failures, etc. Here once again it is mentioned that is arcing horns, yes, when placed or when used, they actually protect the insulators from damage due to tracking. So you just go through this slide. Have you finished?
Yes, sir.
So some more points about arcing horns. Just quickly go through this. Sorry.
Okay, okay, sir.
Okay. Then we have to consider another problem. Can you try yourself this problem? Similar to the previous problem. Here m is equal to 9. So you express V3, V2 in terms of V1, and V1 plus V2 plus V3 will be equal to 33 by root 3. 33 kV is the line voltage. You have to find out the phase voltage first, because it is the voltage is V1, V2, etc. with respect to ground. So from there you can find out V1, and then V2, V3 you can very easily find out, because V2 will be equal to 1 plus 3 by m plus 1 by m square V1, and V3 is also like this. You find out this, work out this, and tell me the results.
Sir, V1 is coming as 5.51 kilovolt.
V2 is 6.12 and
Here are the results.
Yes,
Okay.
sir. Okay.
Okay. Now let me see what are the things left. Okay. So problems we have discussed, other problems you work it out from any book on power systems, transmission and distribution, and also from Parker and Smith. So with this, we conclude our discussion on chapter 1. And after today's class, I shall send you the PPT, not PPT, the, PDF format, in PDF format, the notes on chapter 1. And that will be the way we shall be sending the notes. Actually, after the completion of a particular chapter, the PDF of that chapter will be sent to you. Now let me call your roll numbers. Roll number 1. Roll number 2. Roll number 5.